Hey everybody, thank you for joining our live stream today. Sorry that we're rather late. I would say that we had an urgent customer situation, but really we had a technical issue that marketing were trying to fix. So I'm going to blame marketing entirely. Good to blame somebody. So my name is Jon Wilde. I'm VP of Customer Success here with SimScale. And a little bit about my background, I guess, is that I have a master's in thermodynamics and fluid mechanics. I worked for quite a few years as a real engineer in the defense industry, and then moved pretty quickly to be an application engineer. I wasn't really enjoying 10-year life cycles of products and that kind of stuff, and I wanted to do something faster paced. And then from an application engineer into managing a customer success team, and then on here to SimScale, where I'm essentially running 3 teams, I guess. So like the pre-sales team, the post-sales team, and driving product management as well.
Cool. My name is Matt Bemis. I'm an application engineer here. Been here for going on 6 months. I've been running simulations on a daily basis for 4 years and a little bit more now. Basically, I spend my day helping customers use simulation to build better products.
What is your favorite thing about SimScale, Matt?
Well, I enjoy working for a very international company. It's pretty awesome. Yeah, so many people from different backgrounds. You can't even try to keep track. My favorite thing about the platform is probably the accessibility. So if I left my laptop at home or something, I could just walk up to a computer, sign in, and everything's there. So that's really awesome. What about you?
The uniforms. No, I think you nearly took my joke, I think, but like we have SimScale the company and SimScale the platform. I think my favorite thing about the company is definitely the people. We all really care about the product, and we all care about simulation, and we all care about our customers. And what I like about the product, I think, is that apart from it being cloud-based and all that kind of cool stuff, the fact that it's CFD and FEA and everything all in one place. And I like that. That's kind of unique. And it also means that we have an additional challenge of having to learn everything. Yeah. You can't just learn one thing. You have to be kind of broad, and I like that a lot.
It is neat. Sometimes people may use CFD quite often, but then sometimes, they want to play with FEA, or they get one project a year, but you don't want to go out and buy other software program for that. So Cool. Shall we move on to some questions from social?
Yeah, but you know what I noticed? I can see the screen from here, and I really hate that the screen covers like the fat rolls, and you can really see mine. So I'm going to just suck in for the rest of the broadcast.
I've been jogging.
Yeah, shows. Yeah, sure. We can do. Do you want to start?
Yeah, so we have some questions from LinkedIn. So Alex asked, any chance SimScale is capable of doing painting application simulations? Want to evaluate the thickness, performance during a robotic painting. So this might be like a painting of an automotive body or something like that. I think that type of application would be highly specialized. I don't really think we could accurately predict the very thickness. But what do you think? What could we capture?
Yeah, I think there's some things we could do and some things we can't, right? So we have a good multi-phase solver, so we could look at like large bodies of water and that kind of thing we can model really well and quite quickly. What we can't do, I guess, is moving towards this kind of spraying, right? So when we're looking at the tiny particles, that would be a challenge. So that part of it, which I think is the part you need, probably we couldn't do. But then I guess further downstream, we could look at, say, you've got, assume like a car shell perhaps, and you've got the paint on it, and you could look at the kind of uniform cooling and that kind of stuff. But as far as like looking at the painting and looking at the actual thickness, I think we would struggle.
Yeah, so you could do a heat transfer analysis if there's a certain amount of velocity hitting the body, cooling the part. You could, predict temperature over time, just general, I guess, velocity in different parts of the body.
Yeah.
Cool.
Okay, so the next question is from Roland, which sounds really German to me, being based over here in Germany. It reminds me of an old boss I used to have, actually. The question is, what is the difference between selecting different numbers of processes while like meshing and solving, and what does that mean?
Cool. Yeah, so I'll take that one. So you do have an option when you go to hit mesh. It says number of processors. Really, that's just deciding how much RAM is going to be allocated. So if you say the default is 4, if you get an error message that says you ran out of RAM, just choose 8 or 16, rerun, and then you should be able to get a mesh. Anything you want to add?
I guess maybe thinking about within the solve as well, right? So yeah, you choose it within the mesh, but then what do you do when you solve?
Yeah, so there you have to choose as well. When you're solving, adding more cores will speed up the solve time significantly, kind of depending on the mesh size, but generally you can speed up simulation time.
Okay, and then maybe I would add, say, if you had maybe a 4 million or 8 million element mesh, assuming this is CFD, I would guess.
Yeah.
You would then maybe run, say, using 8 or 16 cores. So you would kind of double the million elements. And then if you did run on 16 cores, you could probably get roughly, you could like halve the runtime by running on 32 cores.
Yeah.
Right, normally. But it's not an exact kind of trade-off. So you would probably overall, I guess, use more core hours than you would with a 16 core run. But you would get it in roughly half the time. So it's like a little bit of a trade-off between speed and cost efficiency.
Yeah, I will note, the novice CFD user will go out, make a model that says maybe has 30,000 cells, and then run it on 96 cores. Doesn't really speed up the simulation. It takes time to break the mesh apart and to allocate it to different cores. And there is a limit on how much scale you get there. So.
Mm-hmm. Yeah, I tried to make an example of that before. So if you had like a really kind of simple task to do,
yeah.
and you had 4 people doing that task,
yeah,
it's kind of the same kind of distribution of tasks, right? If you had from like 4 to 96 cores, if you had 4 people doing a task,
yeah.
it's really easy to keep them organized.
Yeah.
But to get 96 people organized, you have to really kind of spend a lot of time on the organization, which is kind of like distributing the job over loads of cores, right? So unless it's a massive job, the trade-off isn't really valuable.
If you're making dinner, you don't want to have 96 people helping you.
True. Unless they're all serving you. That now I could do with.
Cool.
Okay. Next question I can tackle too, I think, is from James. I think also from LinkedIn, is what is the convergence plot? So if you're not familiar with SimScale, I guess the convergence plot, once you've started your simulation running, you'll see like a graph being produced along the bottom of the screen. And it will show you different variables like velocity, pressure, maybe temperature if you're running with heat transfer. And what it's actually telling you is what is happening within the solver. So these are like the residuals from one iteration to the next. And really the thing to know, I think, is that you want all of these lines to be trending towards a very small value. So the error from one step to the next is pretty small.
Yeah.
And then once they're all hopefully kind of flat and very low values, the solver should either stop automatically or you can stop it also. And you should then at that point feel pretty confident in your results.
Cool. Awesome.
Yeah.
So moving on to Twitter.
Yeah, why not?
Awesome. So we recently had a webinar on our lattice Boltzmann solver looking at pedestrian wind comfort, and someone responded on Twitter with a question. You want to read it?
Yeah, sure. So the plot was of a city showing velocity flowing through the city. So the red parts are high velocity, the blue parts are very low velocity. And there's loads of like red kind of balls all over kind of the city, or red dots, I guess, depending on how you are looking at it. And the question was, what do those points all represent?
Yeah. So those really, they're just data points that we're probing. So this was based off a technical paper where they did a wind tunnel test and there was, pressure taps there or whatever. So really we're just highlighting in the domain where we sampling the data. And we'll of course, reply with the link to the question as well as an answer after this.
Cool. I think the other thing maybe to add as well is that if you do want to run a city model, you could run, like they do in the wind tunnels, with like a few hundred up to maybe 1,000 or so points where they're going to measure the wind speed and also transiently the gust speed, like through the different parts of the city. Once it's running, also like a convergence plot, right? You could say, okay, I want to monitor this point.
Yeah.
And you could say like, you could basically, as it's going, watch the flow speed.
Yeah.
Right. So you would get an idea of what the maximum gust is and the minimum, if it's going in different directions.
Yeah, absolutely.
Cool. And then you can obviously download all of that data as well if you're using the LBM solver.
Cool.
Yeah. There's a question from Facebook from Alexander, and it says, my design includes a special material that isn't in your material database, our material database. How can we add it?
Awesome. So all you have to do really is just assign one of our default materials and then just start editing. So right in the user interface, you can rename the material, add in density, conductivity, viscosity, all those, and just hit save. So easy as that.
Cool. There's also a question from YouTube, which we'll see. I can also talk to this as well. Basically, it says, I'll read it exactly actually. Hello, I'm working on a CFD simulation. I'm having external suction fans outside of a card cage or outside of an electronics box. How can I create the box envelope, which will define the flow of the air inside the envelope? That's what it says.
Okay.
I think what it means is I've got an electronics box.
Yeah.
How can I capture the air inside? Right?
Now what?
Because it doesn't come from CAD.
Yeah, absolutely. So we recently, a few months ago, put in a FlowVolume Extraction tool, which is really awesome. So if you have an inlet and outlet to your electronics box, but you don't have you need a CAD body basically with air. So we put a tool in there under geometry where you can extract the flow volume. So you would basically select the inlet face and the outlet face. They can be completely open. That's fine. And then you select the seed face. The seed face is just a face which the fluid will be touching. Hit go. It takes about a minute or less, and it generates your fluid volume.
I think maybe important to mention too is actually there's two things I want to say. One is do SimScale users like the naming FlowVolume Extraction? Like, you're welcome to leave comments, right? Because I'm not sure myself.
Yeah.
And also it's not that easy to find sometimes. So in the top of the tree next to geometry, so once you've uploaded your CAD file, there's a tiny kind of button, and there you've got three options for the flow volume extraction, right? So you can create an inner region, so an open region.
Yep.
If the ends are already open, like in this case, I would think.
Yep.
A closed region. So if you've got a room like we're sitting in and it's sealed, then you need to build the air inside. Or an enclosure. So maybe you've got like an aircraft, for example, and you want to run the flow around it. So you could use the enclosure to make this kind of big wind tunnel.
A bounding box.
A bounding box.
Yeah. The other weird thing or little odd thing is you have to actually have your cursor over the geometry body, the CAD body, to have that button show up. So
that's true. That's true. That's changing soon.
I'll hold you to it.
Yeah, it's going to be cool.
It's going to be awesome.
Yeah. Okay. So another question as well from YouTube was how to do a validation of a transient thermal analysis of a steam turbine casing. Hey, I'll let you answer that one. Why not?
Okay. So steam turbine casing, that sounds like basically an FEA, so solid mechanics analysis, I would guess. It sounds like it's going to be a thermomechanical. So what's the stress look like as parts deform due to temperature? Transient, certainly not too bad, especially in solid mechanics. And for heat conduction, heat transfer, you can use pretty large time steps. So yeah, I think if you need help setting it up, reach out to us in chat maybe.
Mm-hmm.
We have in product chat. I would say maybe run a steady state one first and see if you can pull that off before you try to tackle a transient one. But definitely in the realm of what we do. Yeah,
but I think there's also one thing to add as well. I think just to make sure you find it. So when you're using the product, in the bottom right-hand corner, there's like a little speech bubble, and that is the link to take you to the chat, and a box will pop up. In fact, I think I'm online right now on my phone, which I'm not actually going to look at, so don't chat right now. But there should be like at least 5 or 6 people online all of the time, and you can see our photographs, and then just start typing. It depends on your type of account, but your project is either community, so everyone can see, or it's private and nobody can see. So if you also tick share with support, then we can access the project, right? And then
Yeah.
we can immediately, without having to share files and stuff, we can just jump straight into your project and start giving you advice.
Which is pretty awesome. We've used desktop simulation tools, and it's send me your files and I'll get back to you on email.
Yeah, that sucks.
Yeah.
We're not going back to that.
Yeah.
Cool.
I'll read a few.
Sure.
So we have a few live questions now. So we have one that says, is SimScale suitable for academic projects such as robotics? Are there any advantages for students?
Interesting question. It depends what you want to do with robots, I guess. But yeah, fundamentally, so SimScale can do a lot of things in one place, right? So it could do, if you have robotics, you could look at things moving, or you could look at stresses and strains within solid parts.
Yeah.
So like the kind of structural side, the thermomechanical side, like you spoke about, just do parts get too hot or too cold as they're running, depending on the atmosphere they're working within. Then you could also look at CFD, right? So again, like do parts get too hot or too cold based on the surrounding atmosphere?
Electronics cooling is big for robotics.
Yep.
Cool.
Makes a lot of sense, exactly. And other advantages for students, I would say
it's free and we support them. So
yeah.
Absolutely. Yeah.
Yeah. This is the crazy thing that we are still doing, which I think is amazing. And this is another thing I love about us, actually, is that it's free, exactly. And you have a pretty good amount of core hours to use. And yeah, you can still use the in-product chat and you can still ask us for help, which is cool.
Awesome.
Insane, but cool.
Yeah.
I don't know how to read this next question.
Yeah, sure.
I think the question actually might be looking at view visibility. I think it's probably to do with smoke simulations, right? And can we look at visibility within rooms if we have smoke?
Yeah.
I guess there's like a mix of things we can and can't do. So I don't know if we can look at exact visibility.
Right.
But you could model like smoke being kind of distributed into rooms.
Yeah.
So a little bit of a balance between the two.
Yeah. So we support scalar mixing, and that's how I would tackle that.
Yeah, exactly.
Cool.
Okay.
I like this question. So can we start simulations from the last time step? So if I run for 500 iterations, can I restart? Maybe it's not converged enough, something like that. And I bet the development team would love that. Love to get some notice here, but yes, it's new. For most of the types of analysis, you can continue the run. So if you stop, want to take a look at something and then want to restart, no problem. Don't have to run from zero.
But there is a problem as well, right? So
Yeah.
like a little one or a big one, depends on what you need to do. But you can't change the setup yet.
Yeah.
So that isn't yet available, but you can stop and start. So
Yeah.
we're halfway.
Sure.
I think we've done the hard bit.
Yeah.
Or we've done the easy bit.
I haven't done any bit of it.
This is somebody saying that they hope they can use SimScale soon. I hope so too. I mean, if you are at your computer right now, you could also use it right now.
Yeah.
It's free.
Sign
like
up.
Said. Yeah, I think so. There's a question also about modeling at below freezing. I would say mainly yes. It depends what you need to do exactly below freezing. But yeah, there's pretty much no reason and no limit that I could think of.
Yeah. Agreed.
Yeah.
Cool.
Okay. Don't think we have any other questions right now that I can see. Oh no, hang on. There's a couple. Okay. Yeah, we can cover those.
This is my favorite.
Yeah, let me read it out. So which one's your favorite? There's two.
Steady state versus transient.
Okay, you've asked yourself the question. What's the difference between steady state and transient simulations?
Okay, so transient, a lot of people just try to jump to transient because, yeah, in real life it is time. But really, the answer you're trying to get to when you're running a transient analysis is, what's the ramp up look like? How does it change over time? So maybe if your example is an electronics cooling box, transient would be, okay, after 10 seconds, I turn it on and wait 10 seconds. What's the thermal distribution look like? Steady state is just, okay, I've been working on my computer for 8 hours. Nothing's really changing. What's the CPU temperature?
So it's kind of like the infinite transient, right?
Yeah, exactly. After ramp up, just if you were to run transient for 100,000 seconds or something crazy, what's the temperature? Or what's the, what's the results look like? And I'm a big fan of running steady state simulations if you can first, and then chasing transient. It can save a lot of time in setup errors or mesh errors, things like that.
Yeah, I think the same. It definitely makes sense to kind of validate that your mesh is good, that your approach is good.
Boundary conditions are good.
Yeah, exactly. Before you jump into transient and then add like more kind of potential problems, right? So find that it works fundamentally, and then kind of step up.
Definitely.
Right? The next question is that I have a nozzle design, and I've uploaded it to SimScale, but I don't know what to do next. So I assume that they've probably got like just a solid nozzle, right? Like the external part from CAD. And then what do they do next to analyze it?
Our new tool, FlowVolume Extraction. So really, when you're running a CFD simulation, you don't care about the solid. You really care about the fluid around it. So the nozzle body really isn't doing much, but the flow volume inside it is what you care about. So extract the flow volume. You don't need the solid body. And then start applying boundary conditions on your water, air, or whatever. Make sense?
Cool. Yeah, there's also, I'd say, so that tool is called FlowVolume Extraction.
Yeah.
And if you're on YouTube as well, I guess you are right now, you can also just type that in on the search, right? And there's a very short video that takes you through the 3 different ways of using it.
Yeah.
Unfortunately, you have to listen to my voice again, which I apologize, but still, it is what it is. What can you do? It's DNA. Where can I get a SimScale t-shirt? You could join SimScale. I guess is probably one of the answers, right? Look on our job site. We're often hiring, but you've got to be pretty cool and good looking. Like us, right?
Yeah. I mean, come to Munich.
Yeah. Or Boston.
Yeah.
Or New York. Yeah.
Maybe.
We're growing. Okay. I think that's probably all we have time for.
All right.
We did say that's what she said once, which is excellent. Well done, Matt. Well done, me. Yeah, there's a few remaining questions, but I think we'll answer them in the next session that we run, and that will be announced pretty soon. Don't forget that we're still running our Summer Breeze contest, which is like hashtag SimScale Summer Breeze. Anything else you want to say?
I think that's it. Glad to be here in Munich. I work in Boston, so having a fun time here. And thanks a lot for joining.
Thanks very much. Next time.